Welcome back, everyone. Ready for another deep dive? Today, we're going to be tackling a research paper that delves into some pretty fascinating areas of quantum mechanics. We're talking Bopp quantization, density operators, and even deformation quantization. So buckle up, because we're about to explore how all these concepts intertwine to give us a really unique perspective on mixed states.
Yeah, what I find really intriguing about this paper is how it uses Bopp quantization, which, as you know, isn't exactly the standard approach, to shed new light on density operators. It's like a fresh perspective on how we can represent and analyze those ever-present mixed states that, kind of dominate the quantum world.
Okay, so maybe for some of our listeners who might not be as familiar with Bopp quantization, let's start with a quick recap. It's basically a different way of formulating quantum mechanics, right?
Exactly. It's an alternative to the more commonly used Weil quantization. And, both approaches, they provide valid ways to represent quantum mechanics mathematically, but they use different tools and techniques.
And in this paper, they're using Bopp quantization to specifically look at density operators. Can you remind us why those are so crucial when we're dealing with mixed states?
Absolutely. Density operators are like, they're our mathematical saviors when we're dealing with the messiness of real-world quantum systems. In a perfect world, we'd have pure states, perfectly isolated, well-defined. But in reality, quantum systems, they're constantly interacting with their environment, getting entangled, becoming mixtures of different pure states. So density operators, they give us a way to represent and work with these mixed states mathematically.
So it's like they provide this framework for handling the complexity of quantum systems that aren't, living in isolation. Now, before we dive into the specifics of how this paper uses Bopp quantization, let's maybe take a step back and talk about some of the mathematical foundations that are laid out in the introduction. They start by discussing Weyl-Wigner quantization, which seems to be a key concept throughout the paper.
Yes, Weyl-Wigner quantization is really central to their approach. It basically provides a way to link classical functions to quantum operators, which is essential for bridging the gap between classical and quantum mechanics.
Right, because we're ultimately trying to understand these quantum phenomena, but we often start with classical concepts and then we quantize them. So how does Weyl-Wigner quantization help us make that leap?
Well, in Weyl-Wigner quantization, we use what's called the Wigner function. Think of it as a way to represent a quantum state in phase space, that abstract space where both position and momentum are represented. So the Wigner function allows us to see how a quantum state is distributed across different positions and momenta.
So instead of thinking about a quantum state as just a wave function, we can actually visualize it in this phase space. Which gives us more information about its possible positions.
And momentum.
All right.
Exactly. And the Wigner function, it allows us to connect this phase space representation to the operators that act on quantum states. Remember, operators, they're the mathematical objects that represent physical actions or measurements in quantum mechanics.
Okay, so the Wigner function kind of acts as a bridge between the phase space picture and the operator picture. And this is where Weyl quantization comes in.
Precisely. Weyl quantization gives us this way. To associate a quantum operator with a classical function, using the Wigner function, it's like a recipe, that tells us how to construct a quantum operator from a classical function.
So if we have a classical function that describes, say, the energy of a particle, we can use Weyl quantization to create a corresponding quantum operator for energy.
You got it. And this ability to translate between classical functions and quantum operators is really crucial for understanding how quantum mechanics kind of emerges from classical mechanics.
It's like building a quantum dictionary, translating from the language of classical physics to the language of quantum mechanics. Now, the introduction also mentions the Moyal product, which seems to play a pretty significant role in their analysis. Can you give us a quick explanation of what that is?
Sure. The Moyal product is a way of multiplying functions that takes into account the non-commutative nature of quantum mechanics. So, in the classical world, if you multiply two functions, the order doesn't matter. F times G is the same as G times F. But in quantum mechanics, the order of operations can matter. Operators, they don't always commute, meaning that A times B isn't always equal to B times A. So the Moyal product, it's designed to handle this non-commutativity.
So it's a multiplication rule that respects the quirks of quantum mechanics. And the paper mentions that this Moyal product is intimately connected to the Wigner function. and Weyl quantization, right?
Yes. The Moyal product actually emerges naturally when you're working with Wigner functions.
Okay.
And Weyl quantization, it's a powerful tool for understanding how quantum operators behave and interact in phase space.
Okay, so we've got this foundation of Weyl-Wigner quantization, the Wigner function and the Moyal product. Now let's start digging into how the paper actually applies Bopp quantization to density operators. In the next section, they introduce this concept of a Bopp pseudodifferential operator. Can you explain what that is and why it's important in their approach?
Sure. So in Bopp quantization, we work with what are called shifted position and momentum operators. And these shifted operators, they're at the heart of what makes Bopp quantization distinct from Weyl quantization. A Bopp pseudodifferential operator is essentially a function of these shifted operators.
So instead of using the standard position and momentum operators, we're using these modified versions that have been shifted in some way. What's the rationale behind that?
Well, the shift is it's carefully chosen so that it leads to a specific mathematical structure that's well suited for analyzing certain quantum systems. And the paper actually goes into detail about how they construct these shifted operators and how they relate to the standard operators. They introduce parameters, theta and sigma, that control the amount of shifting.
It sounds like they're carefully tweaking the mathematical framework to gain this new perspective on density operators. So how do these Bopp pseudodifferential operators connect to the concept of density operators?
That's where things start to get really interesting. The paper shows that you can represent density operators in terms of these. Bopp pseudodifferential operators, they define what's called the Bopp symbol, which is essentially a function that characterizes the density operator in the Bopp quantization scheme.
So instead of using the standard matrix representation of a density operator, we're using this Bopp symbol, which is a function of the shifted position and momentum operators.
Exactly. And they go on to prove a key theorem, Theorem 3.1. That establishes a connection between the Bopp symbol and the Wigner function.
Ah, so we're bringing the Wigner function back into the picture. What does this theorem tell us?
This theorem is crucial because it shows that the Bopp symbol can be expressed as a convolution of the Wigner function with a specific Gaussian function.
Wait, a convolution. Can you remind us what that means in this context?
Sure. A convolution essentially means you're taking one function, the Wigner function in this case, and kind of smearing it out using another function, which is a Gaussian in this case. The Gaussian acts like a smoothing kernel, spreading out the Wigner function.
So the Bopp symbol is like a smoothed out version of the Wigner function. Why is that significant?
This connection between the Bopp symbol and the Wigner function is what allows us to link the Bopp quantization picture to the more familiar Weyl quantization picture. It's like we're establishing a mathematical dictionary between these two different ways of representing density operators.
It sounds like we're building up this powerful mathematical framework to analyze density operators from this new Bopp quantization perspective. I'm really intrigued to see where this leads. Before we dive into the next section, though, can you give us a little more insight into the proof of Theorem 3.1?
Of course. The proof involves a series of steps that carefully manipulate the definitions of the Bopp symbol and the Wigner function. They utilize properties of Fourier transforms and Gaussian functions to ultimately arrive at that convolution relationship. It's a beautiful example of how seemingly complex mathematical manipulations can lead to elegant connections between seemingly disparate concepts.
It's remarkable how they've managed to weave together all these different mathematical threads. And this is just the beginning. I'm excited to see what other insights they uncover in the rest of the paper. All right, so we've laid some solid foundation and delved into this concept of Bopp pseudodifferential operators and their relationship to density operators. In the next section of the paper, they dive into the Bopp quantization of observables. What exactly are they trying to achieve here?
Well, in quantum mechanics, observables are the physical quantities that we can measure. You know, things like position, momentum, energy, spin, and so on. And in the standard formulation of quantum mechanics, observables are represented by Hermitian operators. What the paper is doing here is exploring how to represent these observables within the framework of Bopp quantization.
So they're essentially translating the concept of observables into the language of Bopp quantization.
Exactly. They define something called the Bopp quantization of an observable, which is a specific Bopp pseudodifferential operator associated with that observable.
And how do they go about constructing this Bopp quantization of an observable? It sounds like it must involve those shifted position and momentum operators we talked about earlier.
You're right on the mark. They use a procedure that involves expressing the classical function corresponding to the observable. In terms of the shifted position and momentum operators, it's a bit like taking the classical representation of the observable and boppifying it, if you will.
So they're essentially adapting the classical representation of the observable to fit within the Bopp quantization framework. Now, the paper introduces a specific example, the Bopp quantization of the Hamiltonian, which, as you know, is the operator that represents the total energy of a system. Can you walk us through this example?
Of course. The Hamiltonian is a fundamental concept in both classical and quantum mechanics. In this example, they consider a Hamiltonian that has both kinetic energy and potential energy terms. The kinetic energy term involves the momentum operator squared, and the potential energy term is some function of the position operator.
Right, so a pretty standard form for a Hamiltonian. How do they go about Bopp quantizing this Hamiltonian?
They apply the procedure we discussed earlier, substituting the shifted position and momentum operators into the classical expression for the Hamiltonian. The resulting Bopp quantized Hamiltonian is a Bopp pseudodifferential operator that incorporates those shifts.
And what's the significance of this Bopp quantized Hamiltonian? What can we learn from it?
This Bopp quantized Hamiltonian is crucial for understanding the dynamics of quantum systems within the Bopp quantization framework, just like in standard quantum mechanics. The Hamiltonian governs how quantum states evolve over time.
So it's like the engine that drives the evolution of the system. Now, the paper also delves into the concept of a Bopp quantum dynamics equation. What is that, and how does it relate to the Bopp quantized Hamiltonian?
The Bopp quantum dynamics equation is the Bopp quantization counterpart to the Schrödinger equation in standard quantum mechanics. It's a differential equation that describes how the state of a quantum system changes over time in the Bopp quantization picture. And just like in the Schrödinger equation, the Bopp quantized Hamiltonian plays a central role in this dynamics equation.
So it's essentially the Bopp quantization version of the equation. That tells us how quantum states evolve. And I'm guessing this dynamics equation is going to involve the Moyal product we talked about earlier.
You guessed it. The Moyal product naturally arises in this equation because it captures the non-commutative nature of the Bopp quantized operators.
It seems like the Moyal product is the key to unlocking a lot of the interesting features of Bopp quantization. Now, in the next section, the paper introduces something called the Stratonovich-Weil quantizer. Can you explain what that is and how it fits into their overall approach?
The Stratonovich-Weil quantizer is a mathematical tool that allows us to connect the Bopp quantization picture to the Weil quantization picture.
Yeah.
Remember we talked about how the Bopp symbol, which represents a density operator in Bopp quantization, can be expressed as a convolution of the Wigner function with a Gosson.
Yes, that was a key result from Theorem 3.1.
Right. Well, the Stratonovich-Weil quantizer provides a way to express the Bopp symbol directly in terms of the Wigner function, without the convolution. It's like a more direct translation between the two pictures.
So it's a way to bypass that smoothing step and get a more precise relationship between the Bopp symbol and the Wigner function.
Exactly. And they prove another important theorem, Theorem 4.1. That establishes this relationship. It shows that applying the Stratonovich-Weil quantizer to the Wigner function gives you the Bopp symbol.
That's pretty remarkable. It seems like they're constantly finding these elegant connections between seemingly different concepts. Before we move on, though, can you give us a little more detail about the proof of Theorem 4.1?
The proof involves a clever combination of techniques. They start with the definition of the Stratonovich-Weil quantizer and carefully manipulate it using properties of Fourier transforms, Gaussian functions, and the Baker-Campbell-Hausdorff formula. It's a beautiful example of how seemingly complex mathematical tools can be used to reveal deep connections between different areas of quantum mechanics.
It's amazing how they're able to navigate through this mathematical landscape with such precision. And this theorem seems to be a pivotal result that will underpin their further analysis. In the next section, they delve into the concept of deformation quantization. Can you give us a brief overview of what that is and why they're bringing it into the picture? Deformation quantization is a powerful mathematical framework that provides a way to formally deform classical mechanics into quantum mechanics. The basic idea is that you start with a classical system, described by classical functions and Poisson brackets, which are a way of defining the dynamics of the system. Then you introduce a parameter, often denoted as Planck's constant, and you deform the classical Poisson brackets into quantum commutators. As you gradually increase the value of saying, you smoothly transition from the classical regime to the quantum regime.
So it's like a mathematical knob that you can turn to dial up the quantumness of the system.
Exactly. And what's fascinating is that the Moyal product emerges naturally. In this deformation quantization picture, it turns out that the Moyal product can be seen as a deformed version of the classical product of functions.
So the Moyal product, which we've been encountering throughout this paper, is actually a key ingredient in this broader framework of deformation quantization. Precisely. It's a fundamental tool for understanding how quantum mechanics emerges from classical mechanics. And in this paper, they're going to use deformation quantization to gain deeper insights into the Bopp quantization of density operators.
I'm really curious to see how they make that connection, but before we dive into the next section, can you give us a little more background on the mathematical underpinnings of deformation quantization?
Certainly. The heart of deformation quantization lies in the concept of a star product. It's a way of multiplying functions. That takes into account the deformation parameter. The Moyal product is one specific example of a star product, but there are other star products as well. The choice of star product depends on the specific system you're studying and the type of deformation you're interested in.
So it's like a family of multiplication rules that are tailored to handle the transition from classical to quantum mechanics.
Exactly. And the beauty of deformation quantization is that it provides a rigorous mathematical framework for understanding this transition and exploring the subtle connections between classical and quantum concepts.
It sounds like an incredibly powerful tool. All right, let's move on to the next section and see how they apply. Deformation quantization to the Bopp quantization of density operators.
Yeah.
Okay, so we've really journeyed deep into this mathematical landscape of Bopp quantization, density operators, and even touched upon this intriguing world of deformation quantization. Now, this final section of the paper, they kind of bring all of these ideas together in this grand synthesis. They're aiming to show how deformation quantization can provide this new perspective on the Bopp quantization of density operators. So what's the key insight here?
Well, the key insight is that the Bopp quantization of a density operator can be understood as a deformation of the classical phase space distribution. Remember how we talked about deformation quantization allows us to smoothly transition from classical mechanics to quantum mechanics by introducing a deformation parameter, Cook.
Yeah, it's like we're gradually turning on the quantumness of the system.
Exactly. What they show in this section is that the Bopp symbol, which represents the density operator in the Bopp quantization scheme, can be seen as a deformation of the classical phase space distribution. So as you increase the deformation parameter, the Bopp symbol becomes increasingly quantum, deviating from the classical distribution.
So the Bopp symbol is like a quantum-enhanced version of the classical phase space distribution.
Precisely. And they derive a beautiful equation that explicitly shows this deformation. It expresses the Bopp symbol as a series expansion in powers with the classical phase space distribution as the leading term.
Can you walk us through this equation? It sounds like it really captures the essence of their approach.
Certainly. The equation looks something like this. Bopp symbol equals classical phase space distribution plus E times term 1 plus E squared times term 2, and so on, where the terms in the series involve derivatives of the classical phase space distribution and the Moyal product.
So the Moyal product is making another appearance. It seems to be weaving its way through all of these different concepts.
It is. The Moyal product is essential here because it captures the non-commutativity of the Bopp quantized operators, which is what gives rise to the quantum corrections, to the classical phase space distribution.
So each term in the series represents a higher order quantum correction.
Exactly. The higher the power of S, the more quantum the correction. And what's remarkable is that this equation, it allows us to see precisely how the quantumness of the system manifests itself in the Bopp symbol.
It's like we're peeling back the layers of quantum reality, one power of S at a time. Now, the paper also mentions something called the Berzin-Toeplitz quantization. How does that relate to their overall approach?
Berzin-Toeplitz quantization is another approach to quantizing classical systems, often used in the context of complex manifolds. It's closely related to the concept of coherent states, which are special quantum states that minimize the uncertainty in both position and momentum. What the paper does is draw a connection between Berzin-Toeplitz quantization and the Bopp quantization of density operators.
So they're showing that there are links between these different quantization schemes.
Yes. They demonstrate that the Bopp symbol can be expressed in terms of the Berzin-Toeplitz symbol, which represents the density operator. In the Berzin-Toeplitz quantization scheme, it's another example of how seemingly different approaches to quantization can be interconnected.
It's fascinating how they're weaving together all of these different strands of quantum theory. Now, the paper concludes with a discussion of some potential applications of their approach. Can you highlight some of the key areas where their work might have an impact?
Certainly. One area where their work could be particularly relevant is in the study of quantum chaos. Quantum chaos deals with the behavior of quantum systems that exhibit chaotic dynamics in their classical counterparts. The Bopp quantization scheme, with its emphasis on phase space representations, and deformation quantization could provide valuable tools for understanding the quantum manifestations of chaos.
So it might help us untangle the mysteries of how quantum systems behave, when their classical counterparts are kind of behaving erratically.
Exactly. Another area where their approach could be useful is in quantum optics, which deals with the interaction of light and matter at the quantum level. The Bopp quantization of density operators could provide new insights into the behavior of light fields and their interaction with atoms and molecules.
So it could potentially lead to new discoveries in areas like lasers, quantum communication, and even quantum computing.
Absolutely. The potential applications are vast. Their work provides a new lens through which we can view and analyze quantum systems, opening up exciting possibilities for both theoretical and experimental advancements.
Well, this has been an incredible deep dive. We've explored a really complex and fascinating landscape of mathematical concepts and their interconnectedness. Before we wrap up, though, I'd like to get your thoughts on the broader significance of this work. What does it tell us about the nature of quantum mechanics and its relationship to classical mechanics?
I think this work beautifully illustrates the power of mathematical abstraction and the elegance of theoretical physics. It shows how seemingly disparate ideas can be connected through rigorous mathematical analysis, revealing deep insights into the workings of the universe. It also highlights the subtle and often surprising relationship between classical mechanics and quantum mechanics. While quantum mechanics is fundamentally different from classical mechanics, there are deep connections between the two, and mathematical tools like deformation quantization allow us to explore those connections.
It's almost as if we're catching glimpses of the underlying mathematical fabric of reality.
Indeed. And the more we explore, the more we realize how much more there is to discover.
Well, I'm certainly feeling inspired to continue exploring. Thank you so much for guiding us through this fascinating journey. It's been a true deep dive.
My pleasure. Always happy to show the wonders of quantum mechanics.
And to our listeners, keep those minds curious and keep exploring the mysteries of the universe. Until next time. Welcome back, everyone. Today we're doing a deep dive on a paper about density operators and Bopp quantization.
Sounds pretty dense.
Well, it is, but it's also super interesting. It's all about representing quantum mechanics in phase space, kind of a different way of looking at things.
I see. And who's the author?
It's Maurice de Gosson.
Oh, of course. From the Austrian Academy of Sciences, right?
Yep, that's him. And, you know, he really gets into the nitty-gritty of the math behind quantum states. But we'll try to unpack it all and make it clear why it matters.
Sounds like a challenge.
Oh, it definitely is.
But
that's what makes these deep dives so fun. Okay, so the paper kicks off with a recap of Weyl calculus.
Weyl calculus, right.
I'm sure we're all familiar with it, but just as a refresher, it's basically a way to connect operators in quantum mechanics to functions in phase space.
Those functions, the symbols.
Exactly. Each Weyl operator has a corresponding symbol. And Weyl calculus lets us figure out how these operators compose, how they act one after the other.
Okay, so that's where the harmonic representation of Weyl operators comes in.
You got it. It gives us this really neat way to see how this composition works.
And that leads us right to the Moyal product.
You know it, the star product.
Yeah, and what's really cool about it is that it's not commutative, meaning the order in which you apply these operators actually makes a difference.
So unlike in classical mechanics, in the quantum world, the order matters.
Exactly. It's one of those fundamental differences that sets quantum mechanics apart.
So the Moyal product is basically a quantum operation, and it seems to have a connection to the Poisson bracket from classical mechanics.
You're right to notice that connection. The Poisson bracket measures how classical observables change relative to each other. The Moyal product is kind of like a quantized version of that.
Oh, interesting. So it links back to those classical ideas. Now, the paper mentions this phase space cyclicity property. What is that exactly?
So if you integrate the Moyal product of two functions over all of phase space, you get the same result as integrating the regular product of those functions.
So the order matters for the star product, but not when you're looking at the overall integral. Why is that important?
It sort of implies that the weirdness of quantum mechanics is localized, and when you look at the big picture, it kind of disappears.
That's deep. And the paper actually proves this property.
It does, using the explicit formula for the Moyal product. It's a pretty involved proof, though.
We'll have to take their word for it then. They also talk about the boundedness of the Moyal product on L1R2N, that function space.
Yeah, that's basically telling us that the Moyal product won't blow up to infinity when you apply it to functions in that space, like a safety net.
Makes sense. But can you give us a concrete example of the Moyal product in action?
Sure. The paper looks at calculating the Moyal product of two cross-Wigner transforms.
Cross-Wigner transforms, right? Those are used to represent the relationship between two quantum states in phase space.
Exactly. So the Moyal product, in this case, tells us about the overlap between those states, which is represented mathematically by the inner product of the wave functions.
Oh, so we're quantifying how much two quantum states mix or interfere with each other using the Moyal product.
Exactly. It's a really handy tool for analyzing quantum interactions.
This is fascinating stuff. Okay, so we've got wheel operators and the Moyal product. What's next on our quantum adventure?
Well, now we're going to shift gears a bit and talk about Bopp operators.
Bopp operators. Okay, this is where it starts to get really complicated, right?
Not necessarily. Think of Bopp operators as kind of like Whale operators in disguise. They have a similar structure but treat phase space variables a bit differently.
Okay, like siblings with similar traits but distinct personalities.
Exactly. Now they're defined through a specific equation.
Ah, equations. Let's hear it.
So we have b hat of f equals the integral over r to n of f of z times t hat of z dz.
Okay, and what are those symbols in that equation?
So f of z is a function on phase space, and those t hats, those are the Heisenberg-Weyl operators.
Right. Heisenberg-Weyl operators. And those are parameterized by a point in phase space.
You got it. Z equals q comma p.
Okay, so it's all connected to phase space. Now, how do these Bopp operators actually relate to Weyl operators?
Well, Schwarz's kernel theorem comes in handy here. It shows how they're connected through a specific integral transform.
Ah, always with the integral transform. So there's a definite mathematical link.
There is. And what's really interesting is that applying a Bopp operator to a function is the same as taking the Moyal product of that function with the operator symbol.
So the Moyal product is showing up again.
It's the glue that holds it all together.
It's everywhere. Okay, so Bopp operators, Weyl operators, Moyal product, they're all intertwined. Where do we go from here?
The paper introduces something called wave packet transforms, which act as bridges between the Weyl and Bopp worlds.
Wave packet transforms? Sounds fancy. So what do they do?
You can think of them as mappings that connect functions in our regular Hilbert space of quantum mechanics to functions in phase space.
Ah, so they're like translators between two different languages.
Perfect analogy. And they're denoted by U sub phi.
U sub phi. Got it. Okay, but how do these wave packet transforms actually create that bridge?
They establish what we call intertwining relations.
Intertwining relations, okay.
Yeah, so basically, you can apply a Weyl operator first, then the wave packet transform, or you can do it the other way around, and you get the same result.
So it doesn't matter which order you do it in.
Exactly. And mathematically, we write it as U phi a hat equals b hat of sigma sub a u phi.
Okay, now I'm lost in the symbols. Can you break that down?
Sure. So a hat represents a Weyl operator, and that sigma sub a is its symbol.
Okay, starting to make sense.
Right. And b hat is, of course, the Bopp operator.
Got it. So we can apply operators in either Hilbert space or phase space, and the wave packet transform ensures that everything stays consistent between the two.
Exactly. It's like a hidden symmetry connecting those two worlds.
That's incredible. But are there any limitations to these wave packet transforms? Can they represent every function in phase space?
That's a great question. And as it turns out, there are some limitations.
Oh.
The paper points out that certain functions, especially Gaussians with really narrow widths, can't be generated using these transforms.
So there's some things they can't capture. Why is that?
It actually ties back to Hardy's uncertainty principle, you know, the one that says we can't perfectly know both the position and momentum of a quantum particle.
Ah, so even our mathematical tools have to obey the laws of quantum mechanics.
Exactly. But don't worry, there's a way to represent every function in phase space. We just need to get a little creative.
Okay, how do we do that?
Well, while a single wave packet transform might not cover everything, if you take combinations of them applied to a complete set of basis functions, You can span the entire phase space.
Oh, I see. So it's like we have a limited set of building blocks, but we can use them to build anything we want.
Precisely.
Very cool. Okay, so we've got this fascinating interplay between Moyal and Bopp operators connected by these wave packet transforms. Now, what about density operators? Those are pretty crucial for representing quantum systems in mixed states.
Absolutely. Density operators, or density matrices, as they're sometimes called, are our go-to when we don't have complete information about the state of a quantum system.
Right. They capture that inherent fuzziness of quantum mechanics.
Exactly. Now, how do these density operators connect with the Weil formalism we've been discussing?
That's a good question. They're definitely related, right?
They are. So density operators on the standard Hilbert space, L2 of Rn, can be represented as Weil operators with specific symbols related to Wigner distributions.
Wigner distributions. Those are those things that represent quantum states in phase space, but they can also be negative, which is kind of strange.
You're remembering correctly. They're what we call quasi-probabilities. It's another one of those quantum quirks.
Right, not your typical probabilities.
Yeah.
So how can we make sense of these Wigner distributions if they aren't really probabilities?
Well, even though they can be negative, they're still incredibly useful for calculating the expected values of observables.
Okay, so we can still extract meaningful information from them. Now, if density operators can be represented in the Weyl framework, what happens if we apply Bopp quantization to them instead? Do we get a Bopp density operator?
No, that's a fantastic question, and it gets to one of the most interesting parts of the paper. Applying Bopp quantization directly to a density operator doesn't actually give you a typical density operator. It throws a bit of a wrench in things because it doesn't behave quite the way we'd expect, especially when it comes to integration.
Doesn't behave quite the way we expect. It sounds ominous. What kind of problems do we run into?
The main issue is that the Bopp quantized density operator doesn't have a finite integral over all of phase space.
So the integral just blows up.
Pretty much. And this is a problem because remember how the Weyl symbol of a density operator is connected to the Wigner distribution?
Right, which integrates to 1.
Exactly. But the Bopp quantized version doesn't do that.
So the Bopp quantization messes up that nice integration property. Does this mean we can't use Bopp quantization for density operators at all?
Not necessarily. The paper gives us a clever way to get around this problem.
Oh, I'm intrigued. What's the trick?
We restrict the Bopp quantized density operator to a special subspace of phase space.
So we're kind of taming it by putting it in a smaller, more controlled environment.
Exactly. And this subspace, we call it H sub phi, is closely related to those wave packet transforms we talked about earlier.
Oh, so everything is connected. And by restricting it to this subspace, it behaves like a proper density operator.
It does. It's pretty remarkable how that works out.
So now we have a restricted Bopp density operator living in this special subspace. What kind of new insights does this give us?
Well, this restricted Bopp density operator has a really elegant mathematical form. It can be expressed using the eigenvalues and projections onto the eigenfunctions within that subspace.
So we've managed to capture the essence of mixed states, but now it's all expressed in the language of phase space.
That's a great way to put it.
It seems like we've really built a bridge between the usual Hilbert space picture and this phase space perspective.
We have. And this bridge lets us bring in the powerful machinery of deformation quantization to help us understand mixed states.
Deformation quantization. That's the framework for connecting classical and quantum mechanics, right? Can you remind me how that works?
Sure. So we start with the algebra of classical observables, functions on phase space that represent physical quantities.
Like position, momentum, energy.
Exactly. And in classical mechanics, these observables combine according to the Poisson bracket.
Right. The Poisson bracket tells us how those quantities change relative to each other.
Yep. Now, deformation quantization wants to deform this classical algebra, meaning we change how these observables combine to capture the non-commutativity of quantum mechanics.
So it's a way to quantize the classical rules.
Precisely. And the prime example of this deformation is our friend, the Moyal product. Remember how it's non-commutative? Well, it can be expressed as a power series in Planck's constant, that fundamental constant of quantum mechanics.
So the Moyal product is like a bridge between the classical and quantum worlds. It's got that deformation built right in.
That's a great way to think about it. Now, the paper brings all of these ideas together. Bopp operators, density operators, and deformation quantization.
Okay, I'm seeing the connection starting to form here. So what's the big takeaway?
The paper derives a really amazing formula that expresses the action of that restricted Bopp density operator on a phase space wave function. And guess what? It involves the Moyal product in a power series expansion.
So the Moyal product, the heart of deformation quantization, is showing up in how these Bopp density operators actually work.
Exactly. It's like we're seeing the connection between classical and quantum mechanics woven into the very fabric of these operators.
This is amazing. We've explored all these different ways to represent position and momentum, delved into Moyal and Bopp operators, encountered those wave packet transforms, and now we've uncovered this deep connection between the Moyal product and mixed states in phase space.
It's quite a journey.
It is. And I have a feeling we're just scratching the surface.
Oh, absolutely. There's so much more to explore here.
Before we dive into the specifics of that restricted Bopp density operator, the paper mentions something called Bopp shifts. What are those exactly, and how do they fit into everything we've been talking about?
Great question. Bopp shifts are actually where this whole area of research started. Fritz Bopp, the mathematician who this quantization is named after, he first proposed them back in 1956. They give us another way to represent those fundamental building blocks of quantum mechanics, the position and momentum operators.
So instead of the usual way of writing those operators, we use these Bopp shifts.
Right. And they look a bit different mathematically.
Can you give me an example?
Sure. Let's take the position operator, usually written as x with a little hat on top. In standard quantum mechanics, it just multiplies a wave function by x. But its Bopp shift, we'll call it x tilde, adds an extra term involving the derivative with respect to momentum, scaled by Planck's constant and the imaginary unit I.
So it's like a combination of the classical position, just multiplying by x, with this quantum twist of a derivative thrown in.
Exactly. And we have a similar Bopp shift for the momentum operator, which involves a derivative with respect to position. The important thing is that these Bopp shifts keep the same commutation relations as the usual position and momentum operators.
Right. Those commutation relations are key to the uncertainty principle.
Precisely. So the fact that Bopp shifts preserve them means they capture that essential quantumness of the operators.
Okay, so Bopp shifts give us a valid but different way to represent those fundamental quantum operators.
Yeah.
But how do they connect to the broader picture of this paper?
The key insight is that Bopp shifts have this special relationship with the cross-Wigner transform. Remember, that's our tool for representing quantum states in phase space.
Yes, it's all coming back to me now.
So the Bopp shifts and the cross-Wigner transform intertwine in a really nice way.
Intertwine meaning they work well together.
Exactly. Applying the standard position or momentum operator to a wave function and then doing the cross-Wigner transform is the same as applying the corresponding Bopp shift directly to the cross-Wigner transform.
So these Bopp shifts, which are different versions of position and momentum operators, are somehow intimately connected to that phase space representation of quantum states.
Exactly. And this connection sets the stage for representing the density operator, which describes mixed states within this whole framework.
Oh, this is getting really exciting. I can't wait to see how this all unfolds.
Me too. It's a fascinating journey.
So tell me, how do they actually accomplish this? How do they represent the density operator in phase space?
Well, the paper dives deep into analyzing the properties of this phase space representation of the density operator and explores how it all ties into deformation quantization.
Deformation quantization, that's where it all comes together.
You got it. And that's where things get really interesting.
I can't wait to hear more.
We'll get there. But first, we need to lay the groundwork. This paper is like a puzzle with all these interconnected pieces.
And we're putting it together piece by piece.
Exactly.
Well, I'm hooked. Let's keep going.
So as I was saying, the paper really digs into how we can represent the density operator in phase space. It's kind of like translating a story from one language to another, except here we're dealing with the language of Hilbert space and the language of phase space.
Right, and we're trying to make sure the story stays the same, even though the words are different.
Exactly. But it's not a straightforward translation.
We've already seen that.
Yeah.
It seems like every time we take a step forward, we encounter a new challenge.
That's the beauty of research. But in this case, the challenge arises when we try to apply Bopp quantization to the density operator directly.
Right, and that's where that pesky integral problem pops up. Can you remind us why that happens again?
Sure. The Bopp quantized density operator just doesn't have a finite integral over all of phase space. It's like trying to fit an infinite amount of stuff into a finite box.
Okay, so it just blows up.
Basically. And that's a problem because we expect the integral to be one, like a proper probability distribution.
Right. That's how the Weyl symbol of a density operator behaves. It connects to the Wigner distribution, which integrates nicely to 1.
Exactly. But the Bopp quantization throws a wrench in the works.
So we can't just directly apply Bopp quantization to the density operator.
Well, not without some modifications. The paper introduces a really clever workaround for this problem.
Okay, let's hear it. How do we tame this unruly operator?
We restrict it.
Restrict it, meaning we don't let it run wild over the entire phase space.
You got it. We confine it to a smaller, more well-behaved subspace of phase space.
Okay, so it's like we're putting it on a leash.
In a way, yes. And this subspace, denoted as H sub pi, has a close connection to those wave packet transforms we talked about earlier.
Ah, so everything's coming full circle.
Exactly. Those wave packet transforms play a crucial role in setting up this restricted space.
Okay, and by confining the Bopp quantized density operator to this subspace, what happens? Does it behave properly?
It does. It becomes a well-defined density operator, just like we want it to be. It's quite remarkable, really.
So now we have this restricted Bopp density operator that's happily living in its designated subspace. What can we do with this new mathematical object?
Well, for one thing, it has a very elegant mathematical form. It can be expressed using the eigenvalues and projections onto the eigenfunctions within that subspace.
It's like we've captured the essence of mixed states, but now it's all framed in the language of phase space, thanks to Bopp quantization and this restriction trick.
Precisely. It gives us a new perspective on how mixed states behave and how they can be represented.
This is fascinating. So we've journeyed from Moyal operators to Bopp operators, explored these intriguing wave packet transforms, and now we've arrived at this restricted Bopp density operator, all within this rich landscape of phase space. It feels like we've built this amazing bridge connecting traditional quantum mechanics to this new way of looking at things.
We have. And this bridge allows us to bring in the power of deformation quantization, which is a really elegant way to connect classical and quantum mechanics to help us understand these mixed states even better.
Deformation quantization. You've mentioned that a few times now, and I have to admit, it still sounds a bit mysterious to me. Can you break it down for us again? How does it actually work?
Of course. At its core, deformation quantization is all about deforming the algebra of classical observables.
Okay, and observables are just those physical quantities we can measure, like position, momentum, energy.
Yeah, you got it. Now, in classical mechanics, these observables are represented by functions on phase space, and they combine with each other according to the Poisson bracket.
Right, the Poisson bracket tells us how these quantities change relative to each other in the classical world.
Exactly. Now, deformation quantization aims to modify this classical algebra to reflect the non-commutative nature of quantum mechanics.
So it's a way to make the classical rules more quantum, so to speak.
That's a great way to put it. And the star of the show in deformation quantization is our old friend, the Moyal product. Remember how it's non-commutative?
Yes. The order matters.
Exactly. And that non-commutativity is crucial for capturing quantum behavior. What's really neat is that the Moyal product can be written as a power series in Planck's constant.
Planck's constant, the fundamental constant that sets the scale for quantum effects. So the Moyal product has this quantum essence baked right into its mathematical structure.
It does. It's like the bridge between the classical and quantum worlds.
This is amazing. The paper connects all these ideas, Bopp operators, density operators, and now deformation quantization. It seems like everything is coming together.
It is, and it gets even better. The paper derives this remarkable formula that expresses how the restricted Bopp density operator acts on a wave function in phase space. And guess what plays a key role in this formula?
I have a feeling I know the answer. The Moyal product.
You got it. The Moyal product appears right at the heart of this formula in a power series expansion.
It's like we're seeing the deep connection between classical and quantum mechanics woven into the fabric of this operator.
Exactly. It's a testament to the elegance and power of mathematical abstraction. It's really quite beautiful.
I agree. This entire deep dive has been an incredible journey. We've explored alternative ways to represent position and momentum, delved into Moyal and Bopp operators, encountered these fascinating wave packet transforms, and now we've uncovered this profound connection between the Moyal product and mixed states in phase space.
It's been quite an adventure, and we're not done yet. There's still much more to explore in this paper.
I'm excited to hear about it. Before we move on, though, I'm curious about something. The paper mentioned a possible connection between this work and the research of Jean Leray. Can you tell us a little bit about that?
Oh, absolutely. Jean Leray was a brilliant mathematician who developed a framework for understanding quantum mechanics using Lagrangian functions.
Lagrangian functions, those are used in classical mechanics, right? They describe the paths that particles take.
Exactly. But Leray found a way to connect them to quantum mechanics. His framework is based on these special geometric objects called Lagrangian submanifolds.
Submanifolds. Okay, now we're getting really into the math.
I know. But it's fascinating stuff. These Lagrangian submanifolds are fundamental in symplectic geometry, which is the mathematical language of classical mechanics.
So it's like we're seeing a connection between classical and quantum mechanics emerging from geometry itself.
Precisely. And the paper hints at a possible link between Leray's work and Bopp quantization. It's an area ripe for further exploration.
Wow, that's incredible. It seems like every time we peel back a layer of this onion, we find even more layers beneath.
That's the beauty of scientific discovery. There's always more to learn, more connections to uncover, and more questions to ask.
This is what makes these deep dives so rewarding. We get to explore these intricate ideas and see how they all fit together, even if it takes a little effort to wrap our heads around them.
Exactly. And it's a reminder that even the most abstract mathematical concepts can have profound implications for our understanding of the universe.
I completely agree. Now, I'm eager to hear about the rest of the paper. What else does it have in store for us?
So where were we? Yes, we were about to uncover the magic of how the density operator, which describes these mixed states, gets represented in this phase space picture we've been building.
Great. It feels like we've laid all this groundwork with Bopp shifts, wave packet transforms, and now it's time to see how it all pays off.
It definitely does. Now, remember how we talked about density operators on the usual Hilbert space being represented as Weyl operators? Well, the paper takes a different route and explores what happens when we apply Bopp quantization to these density operators instead.
So instead of associating a Weyl operator with the density operator, we're looking at its Bopp counterpart.
Exactly. And this shift in perspective yields some really interesting results.
Okay, I'm all ears. Tell me, what kind of insights does this Bopp quantization bring to the table?
Well, it turns out that directly applying Bopp quantization to a density operator doesn't actually give you a standard density operator, at least not at first.
It doesn't. Okay, so what does it give us?
It gives us something that looks a bit different. It behaves a bit strangely, especially when it comes to integration.
You're talking about that integral problem again, right? The one where it diverges.
That's the one. It's kind of a head-scratcher at first. You see, the Bopp quantized density operator doesn't have a finite integral over all of phase space.
Right, and we expect that integral to be one, like a proper probability distribution.
Exactly. That's how the Weyl symbol of a density operator behaves. It connects to the Wigner distribution, which integrates nicely to 1. But the Bopp quantization throws a curveball.
It throws everything off balance.
It does. It makes things a bit messy.
So we can't just naively apply Bopp quantization to the density operator and expect everything to work out smoothly.
Not quite. But thankfully, the paper provides a clever solution to this problem.
Okay, I'm relieved to hear that. What's the trick? How do we fix this?
Restriction. We restrict the Bopp quantized density operator to a special subspace of phase space.
Restriction. So we're kind of putting it in a smaller, more controlled environment where it can't cause as much trouble.
That's a good way to think about it. It's like we're taming a wild beast by putting it in a cage.
A quantum cage. So what's so special about this subspace?
Well, it's denoted by H sub phi, and it's intimately connected to those wave packet transforms we talked about earlier. Remember those? They act like bridges between Hilbert space and phase space.
Oh, right. The U sub phi operators.
Exactly. They play a crucial role in defining this restricted space.
I see. It's all connected. And by confining the Bopp quantized density operator to this subspace, what changes?
The magic happens. Within this restricted space, the Bopp quantized density operator behaves itself. It transforms into a proper, well-defined density operator just the way we want it.
So we've created this restricted Bopp density operator, and it's happily living in its designated subspace. But what's the point of all this? What new insights do we gain from this restricted object?
Quite a lot, actually. For one, this restricted Bopp density operator has a very elegant mathematical form. It can be expressed in terms of the eigenvalues and projections onto the eigenfunctions within that subspace.
Eigenvalues and eigenfunctions, the bread and butter of quantum mechanics. So we're still working within that familiar framework, but now it's all expressed in terms of phase space, thanks to Bopp quantization.
Exactly. It's a powerful way to represent and understand mixed states. And it's just one of the many amazing things that come out of this paper.
This is blowing my mind. It feels like we've embarked on this incredible journey, starting from Moyal operators and Bopp operators, navigating through these wave packet transforms, and now we've arrived at this beautiful representation of the density operator in phase space, all while keeping that crucial connection to deformation quantization.
It's been quite a ride, hasn't it? And it's a testament to the power of mathematical tools for understanding the complexities of quantum mechanics.
Absolutely. I'm incredibly grateful for your guidance through this intricate landscape. And to all their listeners out there, I hope you've enjoyed diving deep into these fascinating ideas with us. Keep those brains buzzing and never stop exploring. Welcome back. Today we're diving deep into an interesting paper. It's at the intersection of quantum mechanics, phase space representation, and Bopp quantization.
Okay, sounds good. I'm ready.
The paper's titled Phase Space Representation of the Density Operator. Bopp Pseudodifferential Calculus and Moyal Product.
Wow, that's quite a title.
Yeah, it is. Haha. It's by Maurice de Gosson from the Austrian Academy of Sciences. And it's a pretty deep dive into the math behind quantum mechanics.
Oh, very cool. I'm always fascinated by how math describes the quantum world.
Yeah, for sure. This paper is perfect for someone with your expertise.
Yeah.
You know, it really gets into the details and equations. Before we jump in, maybe we should just refresh our memories on density operators.
Sure, yeah. Density operators, those are crucial for describing mixed states, right? When we don't have all the information about a quantum system.
Right, exactly. Imagine you've got, I don't know, a bunch of particles, and, some are spin up, some are spin down. But you don't know which ones are which.
Yeah, classic example.
Exactly. That's where density operators come in. They help us represent these mixed states mathematically.
Yeah, they give us a way to handle the probabilities of each state.
Exactly. And this paper, it explores looking at density operators through the lens of Bopp quantization, which is...
I was going to ask about that.
Yeah.
It's different from the more common Moyal quantization, right?
Right. Bopp quantization gives us a unique view of quantum mechanics, but in this abstract space called phase space.
Phase space. Right, where we can represent both position and momentum together.
Exactly. Okay, so with that in mind, let's jump into the paper. Section 1 is the introduction.
Okay, what's the goal? What's de Gosson trying to do?
He wants to present a new way to describe the density operator in phase space, but using this Bopp quantization framework.
So a new language for mixed states, basically?
Yeah. It's like a new language, but rooted in this phase space idea.
Okay, very interesting. And does he meet this into historical context at all?
He does. He mentions Fritz Bopp, who in 1956 introduced Bopp shifts as a new quantization rule.
Interesting. So like a different set of rules for going from classical to quantum mechanics.
Exactly.
I'm familiar with Moyal quantization, but haven't really dug into Bopp quantization much. How do these Bopp shifts relate to things like the cross-Wigner transform, the Moyal product, those more familiar concepts?
Okay, so the cross-Wigner transform, it's a way to take a quantum state, represented by a wave function, and see it in phase space.
Right. Gives you a probability distribution.
Right. Like where a particle is likely to be in both position and momentum.
Yeah. And the Moyal product, that's how we multiply functions in phase space, taking into account the non-commutative nature of quantum mechanics.
Yes. The order matters, right?
It does, unlike in classical mechanics.
Exactly. And what de Gosson points out is that Bopp shifts connect to both of those things. He says Bopp quantization, even though it's less common than Moyal, it can offer a powerful way to understand quantum mechanics in phase space.
I'm seeing why you find this so interesting. Challenging the usual ways of thinking about quantum states in phase space.
Yeah, exactly. Like he's saying, hey, there's this other way, this path that could lead to new insights.
So where does the paper go next after this intro?
The next part dives into the math of Moyal and Bopp pseudodifferential operators, starting with a review of Moyal operator.
Oh, yeah. Those are the mathematical objects that represent quantum observables, right?
Right, exactly. Things we can measure in a system, like position, momentum, energy, that kind of thing.
So a Moyal operator takes a function, the symbol, and connects it to a quantum operator.
Exactly. The paper reminds us about the symplectic Fourier transform and Heisenberg-Weyl displacement operator. They play a big role in defining the Moyal operator. And the Moyal product is back too.
Can we dig into the equations a bit?
Yeah.
Just to make it clear for our listeners.
Okay, so for the Moyal operator, it's denoted by AL, and its action on a function, semi-apex, is given by
I, she, x, 1, a, where a is the symbol of the operator. And it's evaluated the average position and momentum. You see the Heisenberg-Weyl displacement operator in there, shifting things in both position and momentum.
Right. And for the Moyal product, we have AEEEI plus 1 and 2 and 2n. This tells us how to multiply two functions in phase space, A and B, but using the Moyal star product. And this integral captures the non-commutativity, that quantum weirdness.
Right, right. So then the paper brings up Bopp operators. They're represented in a harmonic way, which is different from Weyl.
Yeah, and you can actually think of Bopp operators as special Weyl operators with a twist.
Okay, what kind of twist?
They have a different symbol transformation. The paper gives the formula of the Weyls, AES, PX, XXX. This shows how the Bopp symbol, I, is related to the Weyl symbol, A. It involves these shifts in the position and momentum arguments. And that's why the notation for Bopp operators uses derivatives, because of those shifts.
Gotcha. So built on Weyl, but with this extra layer.
Yeah. And then the paper digs into how Bopp and Weyl operators are intertwined through something called the wave packet transform.
Ah, wave packet transform. That's like a bridge, right?
Yeah.
Connecting the position space representation to phase space?
Exactly. We go back and forth using this transform. It uses the window function, which controls the mapping. Gosson shows that this wave packet transform is key to understanding the relationship between these two types of operators. He gets this formula relating the wave packet transform of a Bopp operator to a particular Weyl operator with a modified symbol.
Okay, so we can translate between the two, Bopp and Weyl, using this wave packet transform as a guide. That's a really cool connection.
It is, and maybe this is a good place to pause. We've covered a lot, and there's still more to discuss, especially about density operators and deformation quantization.
Yeah, agreed. I'm really intrigued to see where this goes.
Me too. Let's pick it up next time.
Sounds good. Okay, so picking up where we left off, I'm really curious about how these density operators come into play. We've talked about Weyl and Bopp operators, but how do they connect to mixed states?
Yeah, that's the heart of Section 3. It focuses specifically on density operators. Gosson starts by reminding us about their role in representing these mixed states. Those situations where we don't have all the info about a quantum system.
Right, like when we have probabilities but not certainties about the state.
Exactly. Like, imagine you've got a box full of, I don't know, coins.
Okay.
And some are heads up, some are tails up, but we don't know which are which.
Yeah, I get it.
In those cases, we need something more than just a simple wave function to describe the system. That's where density operators come in.
Right. They capture the probabilities of all those possible states.
Exactly. And Gosson, he reminds us that we can express any density operator as a sum of projections onto its eigenstates.
Ah, the spectral decomposition?
Yes, each weighted by its eigenvalue. It's like breaking down a complex operator into simpler pieces.
It tells us how the operator acts on the space of states, right?
Right. And he points out that we can represent these density operators as Weyl operators.
Okay.
Where the symbol of that Weyl operator is given by the Wigner distribution of the density operator.
So the Wigner distribution, which is a way to see the quantum state in phase space, becomes the symbol for the Weyl operator. That's pretty neat.
Yeah, it is. But then he brings up this problem. He says if we try to quantize a density operator using Bopp operators instead of Weyl, we run into trouble.
What kind of trouble?
The phase space density associated with the Bopp operator, it ends up being infinite.
Oh, that's not good. Infinite densities are usually a sign that something's gone wrong.
Yeah, it's not physically meaningful, but he finds a solution.
Okay, I'm listening.
He shows that even though the full Bopp operator might not be well defined, its restriction to a specific Hilbert space is...
Hold on, let's back up a bit. A Hilbert space, that's the mathematical space where our quantum states live. So he's saying if we look at a particular subspace of that Hilbert space, the Bopp operator for the density operator makes sense.
Exactly. And the way we define this subspace is through a window function. Remember those from the wave packet transform.
Right, right.
So by choosing this window function carefully, we create a subspace where Bopp quantization of density operators actually works.
That's pretty clever. But why is it so important to represent these density operators using Bopp quantization? What's the advantage over Weyl?
That's a good question. I think it gets to the heart of why this paper is so interesting. Gosson argues that Bopp quantization, even though it's less familiar, offers a fresh perspective on how classical and quantum mechanics are connected.
So by using Bopp quantization for density operators, he's opening up a new way to explore this connection.
Right. And that leads us perfectly into the next section where he introduces deformation quantization.
Deformation quantization, yeah. It's like we're smoothly adding quantumness to our classical world.
I like that. And a key ingredient, according to Gosson, is the Moyal product.
The Moyal product. It keeps coming back.
It does. Gosson shows us how powerful it is for deformation quantization. He proves that the Moyal product can actually be expressed as a formal power series, and it involves the Poisson bracket.
Now, the Poisson bracket, that's a concept from classical mechanics, right?
Yeah, it measures how two quantities change relative to each other.
But how does it fit into this quantum picture?
Well, in deformation quantization, the Poisson bracket takes on a new role. It drives the deformation, it brings non-commutativity into the classical world.
Like it's the ingredient that makes things quantum.
Exactly. Let's look at the formula he presents. He writes AEG, CRRG, AE, AE, AE. So A and B are our classical observables, E is the Moyal product, our quantum multiplication, and Pre is the Poisson bracket operator applied to those observables raised to the power R.
Okay, so the Moyal product is a sum of terms, each involving a higher power of the Poisson bracket. And those higher powers, they represent the quantumness creeping in.
You got it. As Planck's constant goes to zero, we get back the classical product. Then Gosson shows how this all applies to the density operator using Bopp Quantization. He presents this proposition expressing the action of the Bopp phase space density operator on a wave function. It's a series involving the Moyal product between the Wigner distribution of a density operator and the cross-Wigner transform of the wave function.
Okay, lots of pieces coming together here. Can we break that down a bit more?
Sure. So the density operator, remember, describes a mixed state, and the Wigner distribution represents it in phase space.
Yeah, like a map of where the system might be in phase space.
Right. Then the cross-Wigner transform brings in the wave function, representing a single particle, also in phase space.
So both the density operator and the wave function have their phase space versions.
Yeah. The proposition says when we apply the Bopp phase space density operator, denoted by RAS, to a wave function, the result is translinear justly R, where is the Wigner distribution of the density operator, W translinear is the cross-Wigner transform of the wave function with the window function, and Psi is the Poisson bracket operator again.
So this equation tells us that the action of this Bopp density operator on a wave function is a series of terms, each with the Moyal product between the density operator's Wigner distribution and the wave function's cross-Wigner transform. And the powers of the Poisson bracket, those are the quantum corrections.
Exactly. This formula ties together Bopp quantization, deformation quantization, and the phase space view of quantum states. It gives us a powerful way to look at mixed states and how they behave under quantum influences.
This is really remarkable. Bringing these ideas together opens up a new understanding of quantum mechanics in phase space.
I agree. It's a fresh way to analyze quantum systems and their dynamics.
So now we're in the last section, perspectives. It feels like we're at the beginning of something new, ready to explore even more in quantum mechanics. Gosson doesn't just give us answers, he points to new research directions.
Yeah, like a treasure map, but for quantum mechanics.
Exactly. One path leads to Born-Jordan quantization. We've talked about Weil and Bopp, but Born-Jordan offers a whole other perspective.
So we have Weil, Bopp, and now Born-Jordan. Is there an easy way to understand how they're different?
Yeah, good question. Each one has a different way of turning classical stuff into quantum stuff. They disagree on how to order position and momentum operators, which are non-commutative in quantum mechanics.
Right, the order matters.
It does. Weil quantization is the most symmetric balancing position and momentum. Bopp, as we saw, uses shifts, and Born-Jordan, it uses a kind of averaging to deal with operator order.
So Gosson thinks that if we apply deformation quantization to Born-Jordan, we might find new insights into how it bridges classical and quantum.
Exactly, like using a powerful tool to examine a specific area.
Why is Born-Jordan so interesting for this? What makes it special?
It has some unique properties. It's closer to classical statistical mechanics than the others. Exploring deformation quantization within Born-Jordan could help us understand the link between classical and quantum statistics better.
Interesting. It seems like different quantization schemes show us different sides of the relationship between classical and quantum. What other research paths does Gosson suggest?
He also talks about a connection between deformation quantization and Lerais Lagrangian functions. They're a way to represent quantum states geometrically.
Okay, I'm always up for some geometry. How do these Lagrangian functions work?
Imagine a classical system evolving in phase space. It traces out a path, a Lagrangian submanifold, Loray's Lagrangian functions are defined on these submanifolds. They encode information about the quantum state onto those geometric structures.
So instead of thinking about quantum states as abstract things, we can see them as functions in phase space.
Exactly. It connects the geometry of classical mechanics to quantum states.
So that's how it relates to deformation quantization. We can see how these geometric representations change as we move from classical to quantum.
Yes. De Gosson thinks Loray's Lagrangian functions could give us a broader understanding of deformation quantization beyond the standard Moyal product.
Wow, that's taking things a whole new level. We're going from algebra to geometry in quantum mechanics.
It's really exciting. This could give us a deeper understanding of the geometric foundations of quantum mechanics. Imagine seeing how quantum phenomena arise from classical structures in phase space.
This deep dive has been amazing. We started with Bopp Quantization, then explored deformation quantization and the Moyal product.
We saw how they connect classical mechanics to quantum mechanics and how quantum effects come from classical structures.
The Gosson gave us ideas for future research, like applying deformation quantization to Born-Jordan and the connection to Loray's Lagrangian functions.
It feels like we've gotten a glimpse of the future of quantum mechanics, where new mathematical and geometric tools will help us uncover even more mysteries. What were your biggest takeaways? What sparked your interest the most?
For me, it's the realization that there's so many ways to understand quantum mechanics. Whale, Bopp, Born-Jordan, they all offer unique perspectives, and there's this beautiful connection between algebra, geometry, and physics in all of them.
That's a great point. The variety of frameworks in quantum mechanics shows how rich and complex it is. There's always more to discover, more connections to make, and more mysteries to solve. This exploration has left me feeling so energized about the future of quantum mechanics.
Me too. It's a field full of surprises and challenges, and the more we learn, the more we realize how much more there is out there. The relationship between classical and quantum, the dance between algebra and geometry, those are big questions that will keep us fascinated for a long time to come.
Absolutely.
Welcome to another deep dive. This time, we're going deep into Bopp quantization and how it applies to density operators.
It's a fascinating area.
It really is. And our main source material, a research paper, phase space representation of the density operator, Bopp Pseudodifferential calculus and Moyal product.
Quite a mouthful.
Yeah, but it's packed with math. So if you're into that, buckle up.
We're diving deep.
Equations, proofs, the whole works.
It's going to be fun.
So have you ever wondered if there's like a different way to picture those fuzzy mixed states in quantum mechanics?
Besides the usual density matrix?
Exactly. Well, this paper digs into that using something called Bopp quantization.
It's a pretty cool approach.
And to guide us, we have an expert.
Hi, everyone. Glad to be here.
So the paper starts off, right, by introducing this Bopp alternative to the standard quantization rules.
Yep.
And that's where equation 1 comes in. I got to admit, it's a bit of a head-scratcher at first glance. But what's cool is they connect this rule to things we're more familiar with.
Like cross-Wigner transforms.
Right, and Whale operators. It's like they're building a bridge between different mathematical worlds.
It is fascinating how Bopp's approach, which was initially considered, well, maybe a bit too hand-wavy, is now gaining traction. It offers a unique perspective.
From phase space.
Yeah, and it's tied to the Moyal star product and this broader idea of deformation quantization. Like we're looking at quantum mechanics through a new lens.
And it reveals some pretty neat connections.
Yeah.
Okay, you said Moyal product. And honestly, that's where I could use a little help. The paper uses it a lot.
Oh, yeah.
Especially in equations 12 and 13. Can you break it down for us? What is it and why is it so important here?
Absolutely. So the Moyal product, it's denoted by a star symbol, is essentially a way to define multiplication, but between functions on phase space.
Okay.
And it's not your usual commutative multiplication.
Right, because we're in the quantum world.
Exactly. Equations 12 and 13, they show the math behind it.
Yeah, I saw those integrals.
Right, and the symplectic form. That captures the geometry of phase space. But the essence is this. It captures that inherent non-commutativity of quantum observables.
Because in quantum mechanics, the order you measure things matters.
Big time. And the Moyal product, it beautifully captures that non-commutativity in the language of phase space.
So not your grandma's multiplication table. It's like a special rule made just for the quantum world.
Yeah.
Where things, don't play by the classical rules.
Exactly. And because of this unusual multiplication, we get some really interesting properties, like phase space cyclicity.
Jeez.
It's shown in equation 14. Basically, when you integrate the Moyal product of two functions over phase space, it's the same as integrating their regular product. It doesn't matter what order you multiply them under the star operation. And the cyclicity has deep implications for how we understand the dynamics of quantum systems in phase space.
So there's like a hidden symmetry there.
Precisely. And another really important feature is its boundedness. On L1 R2n, as stated in equation 15, this means the Moyal product doesn't explode to infinity, even with functions that have large values.
So it's well-behaved?
Yes. We can work with it without encountering those nasty infinities.
So it's powerful, but also well-tamed. Now, the paper gives a concrete example in Proposition 1, equation 16, to show how to calculate the star product. They use two cross-Wigner transforms. And I gotta say, that proof got a little dense for me.
It can be a bit much.
Could you maybe walk us through the key steps? And what are the big takeaways there?
Of course. So Proposition 1 is if you take the cross-Wigner transforms of four functions from L2 Rn and calculate their star product, the result is another function that belongs to L2 R2n. The proof uses the connection between while symbols and operator kernels. The cross-Wigner transform of two functions is basically the while symbol of an operator whose kernel is formed by the tensor product of those functions.
Okay, so there's a lot of moving parts.
Right, and the proof goes step by step, calculating the kernel of the composite operator that corresponds to the star product of the Weyl symbols. And that leads us to the formula in equation 16.
So it's like translating between different representations.
Yeah, moving between phase space and Hilbert space.
Got it.
The takeaway from Proposition 1 is that the Moyal product, when applied to cross-Wigner transforms, it keeps things within the structure of L2 R2n.
Meaning we stay with well-behaved functions.
Exactly. And that sets the stage for Bopp operators in section 2.2, where things get even more interesting.
I'm ready. So section 2.2 starts with the formal definition of Bopp operators, and equation 20 gives us their harmonic representation. What struck me is how similar it looks to the representation of the Weyl operator back in equation 9.
That similarity is not a coincidence.
Oh, I bet.
Proposition 2 and equation 21 formally establish that a Bopp operator can actually be seen as a while operator, but with a shifted perspective. The proof goes into the math behind this, showing how the while symbol of a Bopp operator relates to the symbol of the corresponding while operator, and it does this through a specific transformation involving the standard symplectic matrix.
So, like looking at the same object but through different lenses.
Perfectly put. And this shift, this Bopp formalism, opens up new ways to analyze quantum systems in phase space.
It's like we've been given a new toolkit. And I can't wait to see what we can do with it. Now, section 2.3 brings in these intertwiners. This concept really caught my attention. Equation 24 defines the wave packet transform U, which acts like a window through which we observe quantum phenomena. What's really fascinating is how U connects to Moyal's identity, equation 25, and why these transforms are so crucial in Bopp calculus, like Proposition 3, equations 26 and 27 highlight.
Right. Well, Moyal's identity is key in phase space quantization. It shows this deep connection between the inner product of two cross-Wigner transforms in L2 R2n and the inner products of the functions themselves in L2 Rn. Basically, the phase space representation captured by the Wigner transform is intimately linked to the standard Hilbert space formulation of quantum mechanics.
Like those two worlds are talking to each other.
Exactly. And the wave packet transform, UFA, it acts as a bridge between those two worlds. It uses the cross-Wigner transform to map functions from L2 Rn, which is the Hilbert space of quantum states, to L2 R2n, the realm of phase space. And then Proposition 3 beautifully demonstrates how Bopp and Weyl operators are intertwined through U, showing that applying a Bopp operator followed by U is the same as applying U followed by the corresponding while operator.
Or they're translating between languages.
Exactly, which helps us understand Bopp operators even better by using what we know about while operators. Now, it's important to note that the Hilbert spaces H generated by U, as useful as they are, they don't cover all of L2 R2n.
Not everything fits.
Right. The paper gives Gaussians as an example. Gaussians that are too sharp violate Hardy's uncertainty principle.
Which basically puts limits on how well we can know both the position and momentum of a particle.
Exactly. And these Gaussians, they can't be expressed as the wave packet transform of any two functions in L2 Rn.
So our window analogy has its limits.
Yes. We can't capture every function in phase space using a single window function.
But Proposition 4 gives us some reassurance.
It does. It states that even though we can't represent every function in L2 R2n using just one window function, we can build an orthonormal basis for L2 R2n by using wave packet transforms with carefully chosen orthonormal bases for L2 Rn.
So multiple windows to get the whole picture, like a mosaic.
Perfect analogy. And this brings us to the heart of the paper, which is the application of Bopp quantization to density operators, Section 3.
Now we're talking. Density operators, they're essential for mixed states, those quantum systems that are a blend of different possibilities. But before we dive into Bopp's approach, let's do a quick recap. Section 3.1 provides a nice overview.
Yeah, it covers how they represent mixed states and their connection to the Wigner distribution and marginal properties.
Right. So density operators, also known as density matrices.
They're vital for quantum statistical mechanics. They provide a way to represent a system that's not in just one pure state, but is a statistical ensemble of multiple pure states.
Each with a certain probability.
Exactly. Mathematically, they're positive, semi-definite operators on L2Rn with trace 1, meaning they have a special kind of positivity, and their eigenvalues sum to 1.
Okay.
They basically hold all the info about the statistical properties of a quantum system.
So it's like a mix of different quantum states.
With each state having its own chance of being observed. And their connection to the Wigner distribution, equation 29, and marginal properties, equations 31 and 32, is crucial. The Wigner distribution gives us a phase-space picture of the density operator, allowing us to see the statistical distribution of quantum states in terms of position and momentum.
Like a map of where the quantum states are hanging out in phase space.
Precisely. Now, Section 3.2 introduces the Bopp quantized density operator, and here's where things get a little tricky. It says this Bopp operator can't actually be considered a density operator in the traditional sense.
Why is that? What's going on there?
Well, the Bopp quantized density operator comes from applying the Bopp quantization procedure to the traditional density operator. In this transformation, it can lead to some unexpected results. The integral of the Bopp quantized density operator is usually infinite, which doesn't fit with how traditional density operators work, where the integral is always 1.
Ah, so it's a normalization issue.
Exactly, but Proposition 6 comes in and clarifies this.
Okay, good, because I was lost. So if the Bopp operator isn't a density operator in the usual sense, how does it represent mixed states? What's the trick?
The trick is that while the Bopp operator itself may not be a density operator on the whole L2 R2n space, when you restrict it to a specific Hilbert space, H chirp, which is denoted as pros, it actually is a density operator. Proposition 6, equation 33, gives the math for this restriction, and it changes everything.
So it's about zooming in on the right subspace.
Yes. Finding that spot where the Bopp operator behaves like it should.
Like finding the right setting for a diamond.
Exactly. And the proof of Proposition 6 uses eigenvalues and projection operators. It shows that Russ meets all the criteria for a density operator within the Hilbert space H. It's positive, semi-definite, has trace 1, and can be expressed in the right form using projection operators.
So we tamed the infinities.
By restricting it to the right subspace, and revealed its true nature as a density operator in disguise.
It's like a mathematical magic trick.
Yeah.
Now, this leads us to the final key section of the paper, deformation quantization, Section 4. This is where we bridge classical and quantum mechanics.
It's a fascinating concept.
I'm ready.
The idea is to start with the classical algebra of observables, which is commutative under regular multiplication. Then we deform it into a non-commutative algebra, which reflects the behavior of quantum observables.
So we're changing the rules of the game.
Exactly. As we go from the classical to the quantum realm. And the Moyal product, with its inherent non-commutativity, plays a big role in this deformation process. Proposition 7, equation 35, shows this connection by expressing the Moyal product as a power series involving the Poisson bracket, a key concept in classical mechanics.
It's like a fusion of classical and quantum concepts.
Precisely. And Proposition 8 ties everything together. It connects the deformation quantization of the density operator to the Bopp phase space density operator and the Wigner distribution, all through the lens of the Moyal product and Poisson brackets.
A grand unified theory of everything we've been discussing.
You could say that, showing how they're all intertwined.
This has been so insightful so far. We've covered a lot. Bopp quantization, the Moyal product, deformation quantization, and how it all applies to density operators. It's like a crash course in advanced quantum mechanics.
We've been busy, but there's still more to explore. The paper ends by talking about potential future directions, and I'm particularly interested in exploring Bopp quantization in the context of Leray Lagrangian functions.
That sounds like a topic for another deep dive.
It does.
It's amazing how one research paper can open up so many new paths.
It really is the beauty of research.
Well, on that note, we'll pause here, come back for part 2 of our deep dive, where we'll dig into those connections to Leray Lagrangian functions.
It's going to be good.
Welcome back to our deep dive into Bopp quantization and density operators. It's been a wild ride so far. We've explored those mathematical foundations, the connection to the Moyal product and deformation quantization, and how it all sheds light on representing mixed states in quantum mechanics.
A lot of ground covered, for sure. We've delved into cross-Wigner transforms, Weil operators, wave packet transforms, even Moyal's identity.
And we even managed to tame those infinities that popped up when we first met the Bopp quantized density operator. Remember that?
Oh, yeah. That was a bit of a head-scratcher.
It seemed like a contradiction, right? But Proposition 6 swooped in and saved the day, showing that when restricted to the right Hilbert space, the Bopp operator actually behaves itself, like a proper density operator should.
It all comes down to mathematical precision. Sometimes those seemingly strange results actually lead us to deeper truths.
Absolutely. It's a good reminder that in quantum mechanics, things aren't always what they seem. Now, before we jump to the paper's conclusion and those hints about Leray Lagrangian functions, I wanted to circle back to something you mentioned earlier about the Hilbert spaces, HE, generated by the wave packet transform. You said they don't fully cover all of L2, R2n, meaning there are some functions in phase space that we just can't capture using these wave packet windows. Could you explain that a bit more?
Sure. So remember, the wave packet transform UFI, it maps functions from L2, Rn, the Hilbert space where our quantum states live, to L2, R2n, the space of functions on phase space. It's like embedding the Hilbert space into phase space. But this embedding, it's not surjective, meaning there are functions in L2, R2n that we can't represent as the wave packet transform of any two functions in L2, Rn.
Like trying to fit a square peg in a round hole.
Exactly. And one way to understand this limitation is through Hardy's uncertainty principle, a fundamental concept in quantum mechanics. It basically sets a limit on how well we can simultaneously know both the position and momentum of a particle. Functions that are too sharply peaked, like certain Gaussians, they actually violate this principle.
Because they try to cram too much information into both position and momentum space.
Right. It's like they exceed the allowed quantum fuzziness.
Quantum mechanics messing with our classical intuition about measurement, as always.
Exactly. And this inherent fuzziness, this uncertainty, it shows up in the limitations of the wave packet transform. We can't just create a window that's super sharp in both position and momentum space. There's a fundamental limit to how much we can localize a function and its Fourier transform at the same time.
So even our mathematical tools have to play by the rules of quantum mechanics. It's humbling, in a way.
It is. Nature sets the boundaries, and we have to work within them. But, as we discussed before, Proposition 4 gives us a bit of hope. It tells us that while we can't capture every function with a single window, we can still build a complete orthonormal basis for L2, R2n by using a collection of wave packet transforms. We just need to choose our window functions carefully.
So multiple windows to see the whole picture, like putting together a mosaic. Each tile revealing a different part of the image.
Precisely. Now, with that understanding of the wave packet transform, its limitations and possibilities, let's go back to Section 3 and dive deeper into applying Bopp quantization to those density operators.
Sounds good. Section 3.1 gave us a nice review of density operators, highlighting how they represent mixed states, those quantum blends of possibilities and their connection to the Wigner distribution and marginal properties. But then Section 3.2 introduced the Bopp quantized density operator. And honestly, I'm still trying to wrap my head around it.
It is a bit tricky. The Bopp quantized density operator, it's not a density operator in the usual sense.
That's what threw me off. It says the integral of the Bopp quantized density operator diverges, which clashes with the whole normalization property of typical density operators, where the integral needs to be 1 to represent a probability distribution.
And this divergence, it comes from the way the Weil symbol of the Bopp operator is defined. Remember equation 21. It involves a transformation of the original density operator's Wigner distribution. And this transformation, while mathematically elegant, can sometimes lead to a symbol with an infinite integral.
Like we stretch the probability distribution too thin.
That's one way to think about it. But as we've seen before, things aren't always what they seem at first glance. Proposition 6 comes in and clarifies this whole situation.
Proposition 6 to the rescue, again. So if the Bopp operator isn't a density operator in the traditional sense, How does it represent mixed states?
The key is this. While the Bopp operator itself may not be a density operator on the entire L2-R2N space, when you restrict it to a particular Hilbert space, HE paper denoted as Rus, it actually is a density operator. Proposition 6, equation 33, lays out the math for this restriction, and it's a game changer.
So it's like finding the right stage for the Bopp operator to perform on, where it can act like a proper density operator.
Exactly. And the proof of Proposition 6 utilizes those elegant properties of eigenvalues and projection operators. It shows that Rus fulfills all the requirements of a density operator within that Hilbert space H. It's positive semi-definite, has trace 1, and can be represented in the right way using those projection operators.
So by focusing on the right subspace, we tamed those infinities and revealed the true nature of the Bopp operator, a density operator in disguise.
You got it. It's a testament to the power of mathematical thinking, finding a way to make sense of something that seemed nonsensical at first, by putting it in the right context.
Like finding the missing puzzle piece that suddenly makes the whole picture clear. This deep dive is taking us on quite a journey, from Bopp quantization to the Moyal product, deformation quantization, and now we've even tamed those troublesome infinities.
We have covered a lot of ground, but there's still more to explore. The final section of the paper hints at connections to even broader areas of mathematical physics, specifically Leray Lagrangian functions.
Okay, before we go there, let's take a moment to recap what we've learned so far. We've explored the foundation of Bopp quantization, its links to the Moyal product and deformation quantization, and how to deal with those tricky infinities that came up with the Bopp quantized density operator. Quite a ride.
It has been. And the journey's not over yet. The last part of the paper promises to link us to even more fascinating areas of mathematical physics.
Well, on that note, let's take a short break and come back for the final part of our deep dive into Bopp quantization and density operators. We'll delve into those intriguing connections to Leray Lagrangian functions. Stay tuned. Welcome back to the final part of our deep dive into Bopp quantization. We've covered so much ground, from the mathematical foundations to the Moyal product, deformation quantization, even those tricky infinities we encountered. It's been an amazing journey.
It really has. We've really explored Bopp quantization and how it offers a unique perspective on quantum states, especially those mixed states.
And we even connected classical and quantum mechanics through deformation quantization. It's incredible how abstract math can illuminate the physical world. But, like any good adventure, there's always more to discover. And this paper, well, it points us towards something really interesting, a connection between Bopp quantization and Leray Lagrangian functions. Now that sounds exciting.
It is. This is where things get even more fascinating. Jean Leray, he was a brilliant French mathematician, and he developed this whole framework for analyzing how classical and quantum mechanics relate through these things called Lagrangian submanifolds and what he called Lagrangian functions. It's a beautiful mix of geometry and analysis.
I'll be honest, Lagrangian functions are a bit outside my expertise. Could you give us a quick rundown? What are they and why should we care about them in the context of Bopp quantization?
Okay, so imagine phase space, right? It's the space where we describe the position and momentum of a particle. Now, a Lagrangian submanifold, it's a special kind of submanifold of that phase space. It captures the dynamics of a system by constraining the possible combinations of position and momentum, like defining the paths a particle can take as it moves through time.
So it's like a blueprint for the motion of a classical system.
Exactly. And Leray Lagrangian functions, they're these formal power series. They're defined on the universal covering of a Lagrangian submanifold. They have a phase function that basically encodes the system's dynamics, telling us how it evolves over time.
Okay, I think I'm starting to get it. It's like a mathematical language for describing the evolution of a classical system, but with this geometric twist.
Precisely. And what's really cool about Leray's work is that it goes beyond the usual Hamiltonian way of looking at classical mechanics. It gives us a framework that naturally extends to the quantum world, offering new insights into how classical and quantum descriptions of systems connect.
So that's where the link to Bopp quantization comes in. We've been talking about how Bopp quantization gives us this phase space view of quantum mechanics. So it seems natural that there might be a connection to Leray's geometric framework.
You got it. The authors of the paper suggest that Bopp quantization, with its focus on phase space, could be a bridge to Leray's ideas. They propose exploring whether the Bopp quantized density operator can be understood in terms of Leray's Lagrangian functions.
So we're looking for a deeper connection between these two approaches, like trying to translate between two different maps of the same territory, hoping to reveal hidden features by combining them.
Exactly. It's a really exciting prospect. Imagine being able to see the evolution of quantum states, not just as these abstract vectors in Hilbert space, but also as trajectories on geometric structures in phase space.
Wow, that would be incredible. It's like merging the abstract world of quantum mechanics with this more intuitive picture of classical trajectories guided by geometry.
Precisely. And the tools of Bopp quantization and Lerais Lagrangian functions might just hold the key to unlocking this deeper understanding. It's definitely a challenging area, but it has the potential to be groundbreaking.
This deep dive has been incredible. We started with the math behind Bopp quantization, explored its connections to the Moyal product and deformation quantization, and even figured out how to deal with those infinities that popped up.
And now we're seeing how it might connect to even bigger ideas in mathematical physics.
It's been amazing exploring this with you, and I hope our listeners have enjoyed the journey. It's a great reminder that even the most abstract math can have a huge impact on how we understand the universe. So until next time, keep exploring, keep questioning, and keep your curiosity alive.
Welcome to another deep dive. Today we're going on a journey. It's into the world of quantum mechanics, but specifically, how we can view it through phase space.
Phase space, huh?
Yeah, you know, that mathematical space, where a system's state is described by its position and momentum. We'll be exploring a paper.
Okay.
It's by Maurice de Gosson.
All right.
It's called Phase Space Representation of the Density Operator, Bopp Pseudodifferential Calculus, and Moyal Product.
Sounds pretty complex.
It is, but fascinating too. The paper's trying to answer a question.
Yeah.
A pretty fundamental one. How can we represent the density operator using the language of phase space?
Ah, the density operator. That's key for describing mixed states. You know those situations where we're not sure about the exact state of a quantum system?
You got it. So get ready for some math.
Yeah.
We'll encounter Bopp operators, the Moyal product, maybe even some deformation quantization.
I'm ready. So where do we begin?
Well, the introduction sets the stage. It dives into what motivated this research. It introduces Bopp quantization.
Bopp quantization.
Yeah, it's an alternative to the standard rules for quantization in quantum mechanics.
Right, standard quantization. It tells us how to go from those classical variables, like position and momentum, to their quantum operator counterparts.
Right. But Bopp quantization, which Fritz Bopp introduced back in 1956, it throws something else in.
Oh, what's that?
Bopp shifts. They modify those usual position and momentum operators.
Yeah.
What's cool is how these shifts connect to something else.
So
Wigner transform.
Oh, yeah, the Wigner transform. That's how we can visualize quantum states in phase space, right? And lets us see those fuzzy quantum states in terms of position and momentum.
Exactly. So Bopp shifts offer a different way of looking at things, how we represent these fundamental quantum operators within phase space.
Okay, I'm starting to see how Bopp quantization could provide a different angle for understanding these quantum concepts. What's next?
Section 2 of the paper. It goes into Moyal and Bopp pseudo-differential operators.
Right.
This is where the math really gets going.
Bring it on. I'm curious about these operators.
So it starts with Moyal operators. They're traditionally used to represent quantum operators in phase space. They rely on something called symbols.
Symbols.
Yeah, they're functions on phase space. They encode information about the operator.
So like a blueprint for how the operator acts on quantum states?
Exactly. Now, to understand how these Moyal operators combine, we have to look at the Moyal product. It's a fascinating thing. It's non-commutative.
Meaning?
The order in which you multiply matters, which is very quantum mechanics.
Oh, non-commutativity, right. That fundamental property of quantum mechanics. It tells us that measurements can affect the outcome, depending on the order that we make them.
You got it. The paper gets into some of the math here.
Oh.
In Proposition 1, it calculates the Moyal product of two cross-Wigner transforms.
Cross-Wigner transforms.
Right, remember, those represent a pair of quantum states in phase space, and it turns out that when you take the Moyal product of two of these transforms, you get another one.
Another cross-Wigner transform.
Yes, multiplied by a factor. It's related to the inner product of the states.
So the Moyal product is weaving these quantum states together in a specific way within phase space.
Exactly. The paper then introduces Bopp operators.
Okay.
They emerge from this Moyal product. They offer a different way to represent those quantum operators. Compared to the Weyl operators, it's like two sides of the same coin, each showing a different part of the quantum world.
So two different ways to represent quantum operators in phase space. Moyal operators and Bopp operators. Are they just different math descriptions of the same thing? Or are there advantages to one or the other?
Great question. And the paper addresses it. In Proposition 3, it highlights the close relationship between the two through what's called the wave packet transform.
Okay.
This transform takes a quantum state and maps it onto a function on phase space. What's interesting is that Bopp operators and Moyal operators are intertwined. Through this wave packet transform, they act together, even though they look different.
Like dancing partners, moving in their own style but in sync.
I like that. And to emphasize this connection even more, Proposition 5 states something. The eigenvalues of corresponding Moyal and Bopp operators are the same.
Eigenvalues.
Right, those special values associated with an operator, often representing measurable quantities in quantum mechanics. So even though the operators look different, they have the same fundamental properties.
Okay, that makes sense.
Now, before we go to Section 3, which gets even more interesting, the paper points something out.
Okay.
Bopp operators aren't just some math thing. They're connected to something deeper.
What's that?
The Moyal product.
Yeah.
Which is at the heart of deformation quantization.
Deformation quantization, that's how we bridge the gap, right?
Between classical and quantum mechanics.
Yeah, by deforming the usual algebraic structure of observables.
Exactly. The Moyal product is the math engine behind it. It introduces the non-commutativity that's so important in quantum mechanics into the world of classical mechanics.
Like adding spice to the otherwise bland world of classical mechanics.
Exactly. So we're ready for Section 3 now, which focuses on density operators. This is where Bopp quantization really shines, ready to keep going.
Absolutely. Can't wait to see how Bopp quantization helps us understand density operators. So, Section 3. The case of density operators, it takes us right to the heart of things.
Density operators, they're key for describing mixed states.
Mixed states, right. Unlike a pure state, which is described by a wave function, a mixed state is like a statistical mixture of possible pure states.
And mixture.
Yeah, like a bag of marbles.
Okay.
Each marble is a different pure state. We know the possible states, but not which one we have.
Good analogy. And the density operator captures this mathematically. It holds all the information about the probabilities of the system being in each state.
Right, and the paper points out that the Wigner distribution is used to represent a density operator.
The Wigner distribution.
Yeah, it's basically the Wigner transform of the density operator. It gives us that phase space picture of the mixture.
So it shows how the probabilities of the different states are spread out over position and momentum.
Right, and here's where Bopp quantization comes in. We can apply it to the density operator, just like other quantum operators.
So we get a Bopp operator.
Yes, associated with the density operator. But the paper makes an interesting point.
Okay.
The density operator has a trace of 1, meaning the sum of its eigenvalues is 1. The Bopp operator doesn't.
That's interesting. Trace of 1 for a density operator makes sense. Since probabilities add up to 1, why wouldn't the Bopp operator have that?
Good question. Proposition 6 addresses that.
Oh, okay.
It says, even though the Bopp operator isn't a density operator on the whole phase space, it becomes a proper one when we restrict it to a Hilbert space.
Hold on. Hilbert space. Remind me what that is. I'm getting a bit lost in the math here.
Sure. It's a mathematical space. Each point represents a possible state of our quantum system. Think of it as a stage for the quantum drama. The Bopp operator only makes sense as a density operator when we look at the states within this specific Hilbert space.
So we're zooming in on a particular region of phase space.
Yes, associated with this Hilbert space. This Hilbert space is defined by a window function.
The window function.
It acts like a spotlight, highlighting a region of phase space.
Okay. So by restricting the Bopp operator, we recover that property of having a trace of 1. It's like we're examining the mixture just within that slice.
That's a great way to put it. Proposition 6 also gives us an expression. For this restricted Bopp operator, it can be written in terms of the eigenvalues and eigenfunctions of the original density operator.
So it's the same mix, but through Bopp quantization.
Right.
Elegant. It shows Bopp quantization offers a way to represent density operators within phase space. Now, Section 4 takes on deformation quantization of the density operator. Ready to dive in.
Absolutely. This is where we see how powerful Bopp quantization is in bridging the gap between those two worlds, classical and quantum mechanics.
This show starts by explaining deformation quantization. This framework helps us move from classical mechanics to the world of quantum mechanics by deforming the classical algebra of observables.
Observables, those measurable quantities.
Like position, momentum, energy.
Right.
In classical mechanics, they're represented by functions, and their algebra is commutative.
Meaning?
The order of multiplication doesn't matter, but in quantum mechanics, observables are operators, and their algebra is non-commutative. Order matters.
Non-commutativity, a hallmark of quantum mechanics. It leads to those mind-bending consequences.
The deformation quantization introduces this non-commutativity into the classical algebra of observables. And the Moyal product plays a key role.
The Moyal product, it's back.
Yeah, it's like that secret ingredient that transforms the world of classical mechanics into the quantum world.
I like that.
The paper explains how the Poisson bracket. It describes how observables evolve over time. It gets deformed into the Moyal product. It's like taking this classical idea and giving it a quantum twist.
The Poisson bracket. It's defined using derivatives of the observables with respect to position and momentum. It captures how quantities are connected. In classical mechanics, deformation quantization transforms it into the Moyal product, which has that non-commutativity. It's a great example of how math, from classical mechanics, can be adapted to fit quantum mechanics.
Proposition 8 brings all this together. It shows the deformation of the density operator can be understood in terms of the Bopp operator and the Moyal product, involving the Wigner distribution.
So it provides a recipe for how to deform the density operator using the Moyal product, linking the Bopp operator and the Wigner distribution.
Exactly. Now, before we wrap up with Section 5, I want to highlight a key takeaway. Deformation quantization isn't just some math trick. It has consequences for how we understand and control quantum systems.
It helps us see how quantum mechanics emerges from classical mechanics as we introduce that non-commutativity through the Moyal product. This has implications for quantum field theory, quantum gravity, where we're pushing the boundaries of our knowledge.
Ready for Section 5? Those future directions.
Absolutely. Lead the way. I'm excited to see what else Bopp quantization can do.
So, Section 5. Perspectives. Looks ahead to what might be next.
The exciting part of a paper, what do they suggest for further research?
Well, they remind us of something. We've mainly focused on deformation quantization using the Moyal star product, a specific way to connect classical and quantum mechanics. But we can do it other ways.
The Moyal product, with its non-commutative nature, it was our recipe for introducing quantumness into the classical world. But there are other options.
Exactly. They highlight one. Born-Jordan quantization.
Born-Jordan quantization.
Yeah.
Another way to connect the two, but with a different mathematical approach.
Right. And it might lead to some differences in the quantum theory.
Subtle, but important.
And here's where it gets interesting. They think Bopp operators could help us in understanding and using Born-Jordan quantization. Like we have this new tool that might help us unlock secrets in other parts of quantum mechanics.
It suggests that Bopp quantization, it's more than just a technique. For a specific problem, it might be more universal.
Now, they also point to another connection, one that links back to some deep mathematical ideas by Jean Leray.
Leray?
He introduced Lagrangian functions, defined on special subspaces of phase space, called Lagrangian submanifolds.
The Lagrangian submanifolds, they're those special subspaces where the symplectic form vanishes. They're crucial in classical mechanics, especially Hamiltonian mechanics. They help us study how systems evolve over time.
Right. And Leray's Lagrangian functions, they're basically power series. They capture how observables behave on these special submanifolds. The interesting thing is, these functions can be connected to something else. Formal power series, the ones that arise in deformation quantization.
It's like we're finding a connection between these seemingly different mathematical ideas. Leray's work was in classical mechanics, but they might have something to say about how we understand the transition to quantum mechanics through deformation quantization.
And the paper suggests Bopp operators could be that bridge, like a new language to translate, between Lagrangian functions and deformation quantization.
So we could use Leray's work
to better understand Bopp quantization and its potential.
Wow.
So we've reached the end of our deep dive, Bopp quantization. At first it seemed abstract, but it offers a new perspective on density operators and deformation quantization, and hints at connections to other areas of math and physics.
A good reminder, even in a field like quantum mechanics, there are always new things to discover.
That's the beauty of science.
Yeah.
It never ends. Each new discovery opens up more possibilities. Thanks for joining me on this deep dive into Bopp Quantization.
It's been great exploring these ideas with you. Quantum mechanics never gets old.
Until next time, keep exploring, keep questioning, and keep diving deep.